Design and analysis of chassis for a FSAE car. Abstract design and analysis of tubular frame chassis for a Formula Student competition involve optimizing various parameters that ultimately affect the vehicle's performance. The focus goes behind achieving high torsional, longitudinal, and lateral stiffness, including strength to withstand various real-time situations performed during race conditions and reducing the number of members, weight, and accommodating a male Percy, 95th percentile, and female Percy, 5th percentile, drivers in it. Here, while choosing the appropriate material, various considerations are taken and selected as per multiple requirements such as mechanical properties, strength to weight ratio, including market availability and price. Keywords component, formatting, style, styling, insert, keywords. Introduction. The main idea of designing tubular frame chassis is to accommodate all vehicle components for the functional aspect of the car and reduce the weight. Furthermore, it requires knowledge regarding the subjects of aerodynamics, transmission, braking, suspension, impact attenuator and materials. 1-4. There are different types of chassis used in Formula cars, namely space frame chassis, ladder frame chassis, and composite monocoque chassis are widely used. 5. The tubes are welded together to create space frame chassis. The ladder frame chassis has a ladder shape and the composite monocoque chassis is made of single composite material. Initially, the design of the roll cage starts with ergonomics. They are then designed according to the 95th percentile male, fitting the driver into the cockpit, accessible to the brake pedal, steering dashboard, and steering wheel. 6. This process also helps find the appropriate planes for placing the bulkhead, front hoop, and main hoop. Later, as per the engine spacing and transmission requirements, a plane is chosen to accommodate the engine head. During the real-time situation, a race car is acted upon by various loads statically and dynamically, generating various stresses needed to absorb the roll cage. These forces cause deformation in multiple portions of it, which are caused by acceleration or braking or cornering or when acted simultaneously. So, to resist these conditions, it needs to be rigid enough. Therefore, various tests are analyzed statically to maximize the strength and keep the driver safer too. The strength of a chassis depends upon factors such as material properties, weld strength, and the tube cross-section. In the general process of material selection, we check the bending strength and bending stiffness for a given cross-section of the available materials or vice versa. Sometimes weaker materials with large cross-sections have high bending stiffness, so finding the right material with the right cross-section can reduce space and the number of tubes used in the structure. 7-8. For the chassis design, modal analysis, vibration analysis, front impact, side impact, torsional rigidity, rollover impact is conducted. This is done in finite element analysis, FEM, to save time and testing expenditure. 9-12. 2. Design and material selection. A design approach. While designing the roll cage, we adopted a method. In the beginning phase, the basic design of the roll cage begins with the ergonomics, where a physical prototype of the 95th percentile male template is made. Then, with its help, we tried to determine the position of the main hoop plane. From there, the brake pedal plane is found out. Here pedal box clearances are given, so that bulkhead planes are obtained. Then, the front hoop plane is decided based on the accessibility of the driver. Then, the engine head plane is determined based on the engine spacing requirements and to accommodate the differential. Here, we changed the orientation of the 95th percentile template to recline position, based on which firewall design is made, so that driver does not strain his backbone. It also helps in decreasing the height of the main hoop, and even brake pedal plane can be moved closer so that driver can easily access pedal box. This process is iterative till the design gets suitable for both 95th percentile male and the driver. This also helps in knowing the height of roll hoops, i.e., front and main hoops, which allows following the 2-in rule during the rollover condition of the car. Finally, in this phase, we get to know the distance between the planes. In the next phase, suspension hardpoints are taken as input. These 16 hardpoints are obtained after performing the kinematic analysis, where wheel parameters such as camber, caster, kingpin inclinations are found, including the wheelbase, track width, and ground clearance. Then, a front hoop is drawn with the help of these points of a certain height that was already fixed before. As the remaining hoop distances are known from the earlier phase, all the hoops line diagrams are drawn. Here, the cockpit cross-sectional template is used to provide sufficient room for the driver to access the gear lever and dashboard. At the same time, the internal cockpit template is used to provide legroom. Finally, we have drawn the line diagram of the whole roll cage as shown in Fig 1. With the help of hard points, proper triangulation of members is done for the distribution of the loads correctly. In the final phase, the tubes are assigned to the line diagram to satisfy the tube requirements per the FSAE rule book. B. Material selection. The selection of proper material is the most crucial part while analyzing the various test conditions of the roll cage. It ultimately affects the vehicle's performance. Here, in the beginning, we gathered the steels of different carbon percentages. In the next step, we compared its mechanical properties, such as flexural modulus EI, buckling strength, etc., and physical properties, such as density, UTS, Poisson ratio, etc., of material, which ultimately helps in improving the stiffness and safety factor of chassis with less weight. In the final step, after filtering the materials, we left with few materials which are available in the market, so, in addition to all the above parameters which are needed to be considered, we have also compared the market cost, availability of each material and finalized the material as AISI 4130. Material strength. Young's modulus, E, 210 GPa. Yield strength, SY, 435 MPa. Ultimate strength, SU, 670 MPa. Table 1, Material strength of AISI 4130. Material strength of weld joint. Yield strength, SY, 180 MPa. Ultimate strength, SU, 300 MPa. Table 2, Strength of weld joint. The figure below shows the color coding of various pipe sizes as per the minimum requirement rules given from the rule book, Super International, FB_V 1.1. Here the red color indicates the roll hoops that are of thickness 2.5 mm, then comes the blue indicates the roll hoop bracing, bulkhead, where these are supporting members of roll hoops which are of thickness 1.65 mm, followed by green, indicates the supporting members for roll hoop bracing which are known as main hoop bracing supports or front hoop bracing supports, and then last one that we used is of 1 mm thickness which is used as a non-essential member. Figure 3 Chassis line diagram. Figure 4 Chassis color coding. The above mentioned are the sizes as per minimum requirement, which is assigned to our roll cage. However, we can use pipes of larger thicknesses. As per our design and analysis point of view, the dimensions we have given support the required application, i.e., torsional stiffness, during the race. After selecting material, analysis is to be performed to ensure its stability under various conditions. In addition, to ensure that the roll cage can fulfill the requirements for a high-performance race car, analysis must be performed during the roll cage design. Thus, it is essential to know about loads that act on the chassis, so that the static analysis can be conducted. The following load cases to be considered. See analysis results and discussions. A. Front impact analysis. Most drivers usually experience 3G force while braking, 2 force accelerating, and 1.5G to 2G while cornering. So based on the real-life conditions, assumptions are made for analyzing every case. Front impact analysis. In front impact analysis, we consider that our vehicle is in static condition and rear side of the car is in fixed position, considering the vehicle speed, 6, as 80 km/h at time impact of 300 millisecond and weight of the vehicle is 280 kilograms. F*T equals m, 6 Vf, final velocity, Vf, is 0 km/h, the resulting force is around 20740 N, but in the real-time application during front impact, there is an energy absorbing material, impact 700, which reduces the effect by 4 times, so extreme conditions at nodes of bulkhead are taken as 4G. Fixtures, rear chassis points are fixed. Loads, force applied on 4 members of bulkhead. Time of impact is 600 millisecond as the collision is between 2 elastic bodies which increase the impact time. Using F*T equals m, 6 Vf, the final velocity, Vf, is 0 km/h, the resulting force is around 10,370 N. By considering the energy absorbed B impact 700 and energy lost due to the inelastic collision, the extreme load on the chassis is 2G force. In the side impact type of analysis, we consider our vehicle is in static condition by fixing both the front and rear suspension points of the car. This forms a fixed beam wherein the loads may act on I. A single point. 2. Uniformly distributed, continuous. Fixtures, front and rear chassis points are fixed aside. Loads, force is applied on the L members of the chassis side impact members, including diagonal members. C. Torsional analysis. This analysis is mainly used to determine the torsional stiffness of the chassis. If our vehicle's front wheel bumps and considering the critical condition of dynamic loading under the front member, this can be calculated by the formula below. Fixtures, rear chassis points are fixed. Loads, torque applied on front chassis points. D-rollover analysis. This analysis concentrated on the vehicle when it got rolled over. When this happens, the kinetic energy is converted to potential energy, taking the impact time equals to 150 millisecond. When this happens, the load on the chassis is around 1.5 g. Fixtures, the base part of the chassis is fixed. Loads, force is applied on the top portion of the front hoop and main hoop. 4. Conclusions: triangulation of chassis at few points made better stress distribution and reducing the weight by removing additional members where stress concentration is low. By reducing the height of center of gravity, increased downforce on vehicle. Torsional stiffness is within safe limits and the FOS of different cases of testing is above 1. The cockpit area increased for better ergonomic conditions, and safety of rider has improved. The engine is changed considering the weight distribution to improve performance. The roll cage also satisfies the basic need of a Formula type car, which is a lower weight to strength ratio. In accounting manufacturing, the design of the car is kept very simple. Thus, it can be concluded that this roll cage demonstrates good strengths in all tests and can be used to make a Formula student race car. V. Acknowledgement: the author would like to thank all the faculty of Department of Mechanical, VUSV College of Engineering for their support and helping hands in equipment for this research.